So with capacitors, we haven't worried yet about the time it takes for the capacitors to charge. They don't immediately, just spontaneously end up with all of that charge on their plates. It would be cool. It takes time to charge. Now, it may not take very much time to charge, but it will take some time to charge. So what we're going to talk about next is the flow of the charges, the actual movement of charge per time. And that is where we get to current. There's two currents that we can talk about. Your book introduces both. Electron current versus just regular plain old current. Electron current is the number of electrons per second that flow. Current is the coulombs per second that flows. Coulombs per second is an ampere. That's the term amps. That's where that comes from. That's the one you're probably familiar with. So current, regular plain old current, we're going to use a capital I to represent it. It is defined as the rate at which charge, number of coulombs, flows per second. So remember the three lines. If you haven't seen that before, it means it's a defined as. So it's not simply just equal to, though it is equal to, but its definition is dq/dt. Now back Benjamin Franklin's time, when they first started talking about electricity and really talking about positive versus negative, they defined current as the flow of positive charges. And that's because they didn't know what a positive charge was versus a negative charge. They didn't know fundamentally what the charges were. So they just said, we'll just call the positive ones the ones that are moving, which is perfectly fine. We use that definition today, even though we know that it's not physically the positive charges that are moving. They're the electrons that are moving, so it's actually the negative charges that are moving. But positive charges moving, say, to your right, mathematically are equivalent to negative charges moving to the left. The negative times the negative is positive. So mathematically it's equivalent, so it doesn't really matter in terms of calling it the positive charges that are moving. Electron current, our book uses a lowercase I to represent it. It's simply the number of electrons over the time. So capital N represents the number of electrons that are moving. T is just the time they move in.
Are you going to put a little I and assume we know it's electron current, or a big I and assume it's a big
And quite honestly, as we work through the problems, we're most often going to be using regular old current.
Because we use I for DC and big I for DC. And I just get mixed up. Beyond belief.
Sorry.
That's okay.
Another way to write electron current is in terms of how fast, on average, the charges are moving. This speed, the average speed at which they move, is called the drift speed. To write our electron current in terms of that, it looks like this. Lowercase n is called the number density. It's the number of electrons per volume that are available to move around in your material. Number density is unique to the material. So it's basically your valence electrons. How many valence electrons are there available to move around? A is the cross-sectional area of the wire or material your charges are moving through. And this V is our drift speed. The drift speed is, on average, how fast the electrons are moving. And they really don't move that fast. They move very, very slowly, and that's because there's a lot of collisions between the electrons and everything else that's in the wire. Now, the whole reason we get current, whether we talk about electron current or regular current, the whole reason we get current is if we have an electric field in the circuit. That electric field exerts a force on the charges, thus accelerating them and making them move. We know the electric force is QE. Now it's electrons that are moving, and we know that Q, charge on the electron, is the fundamental unit of charge, so lowercase e. So I can write that as lowercase e, meaning the fundamental unit of charge, the charge on an electron, times big E, the electric field. So there has to be an electric field in order for the charges to move. They have to feel a force, otherwise there's nothing to move them. Now we know that force, according to Newton's second law, results in an acceleration. So the charges end up moving. That acceleration is simply the little e, the fundamental unit of charge, times big E, the electric field, over m, the mass of the electron. Now, average acceleration is simply speed over time. So we can relate this to the drift speed over time. This time is specific. Our book uses a tau to represent it. This is the average time between collisions. So the electric field accelerates the charge until that charge runs into something else. And then it can accelerate it again until it runs into something else. So what we can do here is we can say the drift speed is equal to little e times big E times tau over m. Plugging that in our equation up there, that makes our electron current equal to our number density times our area times what we just derived. For the drift speed. So basically, the electron current that stuff inside the parentheses, the number density, tau, those are specific to your material. Copper is going to have a specific number density, a specific average time between collisions, versus aluminum versus brass. E, little e, and m represent quantities of the electron. The charge of the electron and the mass of the electron, which are constants. That's something we know. Capital A is the cross-sectional area, and big E is the electric field. So there's a direct linear relationship between the electric field and the current that flows. The electric field causes the current. Now to bring that over here, it's really easy actually to figure out current, regular current in amps from electron current. If this is number of electrons per second and this is number of coulombs per second, how can we make the jump between the two? Fundamental unit of charge. If we multiply this by the charge per electron, that's going to give us coulombs per second. So basically, regular current is simply the charge on an electron times that electron current. So basically it is, and we have E squared now, tau over m. Again, all that stuff is either dependent upon the properties of an electron itself or the material properties. This stuff in here value we come up with is called the conductivity. Our book uses a sigma to represent it. It's something unique to the material. Each material has a unique number density and average time between collisions.
What is it called?
Conductivity?
No, the symbol.
Oh, sigma. So sigma is the symbol we use to represent it. Basically, what conductivity is it tells us how good of a conductor our material is. The bigger the conductivity value, the better conductor you have. The smaller the conductivity value, the not so good conductor you have. Okay? That's basically what it tells us. It's a material property. This equation I'm going to bring the A under. I'm just going to go ahead and put sigma in for all that stuff rather than write all that stuff again. This equation is called Ohm's law. For those of you who have electricity experience, this is not the version you've seen, probably. But this is the original version of Ohm's law. What you've used is derived from this equation. Another common way to see this, rather than talk about conductivity, sometimes we write the equation in terms of what we call the resistivity.
They do that with rho.
Yes, I know. I haven't seen rho enough yet this semester, obviously. Just got to throw it in again. So a big conductivity value would correlate to a small resistivity value. So resistivity values. The bigger the resistivity value, the better your material is at resisting the flow of current. It doesn't let very much current flow through it. A small resistivity value means it doesn't resist very much at all.
Just to measure the ohms, right?
This is not resistance.
That's resistivity.
This is resistivity.
Does it have?
It has units of ohm meters, I believe.
Oh, okay. Or is it ohms per meter?
That's what I'm trying to figure out. It's ohm meters. Resistivity and conductivity, these values are unique to the materials themselves. There's a little table in our book that has a few resistivity and conductivity values for a few common materials. Technically, resistivity changes with temperature. As temperature goes up, the resistivity tends to go up as well. We're not going to worry about temperature changes at this point. We're just going to go ahead and assume our resistivity stays constant.